Leader here is Ms. Bonnie Eisenhammer. She is the head of our education group within the Office of Public Outreach at the Space Telescope Science Institute, and we're from Baltimore, Maryland. We have done this workshop 3 years in a row. This year, however, we are especially called out in the grant. And how many more years do we have? We've got two more years after this, so we'll be doing this again. Now, I understand some of you have been here before. How many of you were here last year? All right, thought I recognized you. She was the troublemaker last year. Put your hands up again for these here last year. We want to get a rough count, so we got about 15. That looks like. Anybody here the year before that? Ooh, you guys are just. So you guys were here, and the year before that? I got 1, 2. Okay. All right, you guys are diehards. Well, you have heard us talk about a variety of things, and last year we did a focus on the James Webb Space Telescope. Today's focus is going to be on the solar system. There's something we know and love, but today you're going to find out how much you don't know about the solar system, how much new stuff there is to know about the solar system, and you're going to learn to love it even more. We're going to begin with Dr. BonnieMeinke talking about Saturn. She's an incredible expert on Saturn. We don't have that many planetary scientists at Space Telescope, so she's a very valuable commodity. After that, we're going to spend a session talking about misconceptions. What you think you know, but you don't actually know, and how to work with your misconceptions in your students. After lunch, we're going to do a fun data exercise, a scientific inquiry-based method of looking at the solar system just through the data of the solar system. All right, not looking at all these pretty pictures. Let's look at some numbers and see what we can figure out about the solar system from that. And then we're going to finish up with my talk at the end of the day called "It's Not Your Parents' Solar System," which we talk to you about the changes that we have in our understanding of the solar system that happened over the last 2 decades. Let me introduce the team here. Dan McAllister, stand up. Dan is a teacher of...
I remember a lot of you guys.
Dan, you did like 25 years of high school and math?
We don't go there.
Okay. He's got experience. All right. We'll get these things. Holly Ryer, also a teacher who's working with us. Mick Watkins. You were an intern last summer. Are you still an intern this summer? You still count as an intern? All right. But you've been around, so we don't really think of you. Caitlin, I don't remember your last name. Brecklin, that's right. Another astronomer who is working with us, Brandon Lawton. Okay. All right. So, without further ado, Bonnie, take it over, and Saturn. You want that? Okay, great.
All right. So, sounds like you guys already have a lot of energy. So, if you want to ask questions, shout them out. I'm happy to answer at any point during the talk. Feel free to interrupt me if you don't understand something, and if you can't hear me, let me know. I'll speak louder, or I'll pick up the microphone. Okay? All right, so today I'm taking you guys on a tour.
Do you need any assistance as it relates to lighting?
If you can turn off the front lights, that might help the picture. I don't want to put you guys asleep, though. Okay.
We found something to search.
There's a lot of good images, so I want you guys able to see it. Okay. So I'm taking you guys on a tour of Saturn's rings today, and I want you to think about Saturn's rings as a mini solar system. A lot of people see Saturn's rings all the time in all these great pictures from Hubble, from Voyager, from Cassini, and so it's time to put a little context to those. So first I want to mention that planetary systems are everywhere. In the last 20 years, we've found almost 900 confirmed planets around other stars. That means there's a lot of little solar systems out there. The Kepler mission, which is a space telescope that looks at stars to see their light blinking out as planets pass in front of those stars. that has found 132 confirmed planets in the last 3 years alone, and has over 3,200 planets that are not confirmed. They're candidates, which just means that it takes a little bit longer. We need to build up a little bit more data. I see your question already.
Are we going to consider talking?
Yes, Frank has stuff on a web page, and he will give you the address later in the day.
But since I know you all have your iPads, we're not going to give you that web address until the end of the day because we know you'd be surfing it during the day.
So we'll give it to you at the end of the day. So I just want to let you guys put this in context. There are lots and lots of planets out there. And we've known about these planets only for the last 20 years, but we've seen these protoplanetary disks for even longer, okay? This, for example, is one we've known about for a long time. It's called Fomalhaut. And you can see here, this ring here, that's all dusty debris. The star has been blocked out, but this is where the star would be, that little center point. And then we see this little planet right here within this little box. We've traced it out in several observations. So we know that these other systems happen, and that one of the tracers of them are these dusty disks that happen around the central star. So the structure in these disks is what lets us know there are planets there. Okay, this one, for example, has these arms, right? You see the swirls? It's not just a solid circular annular disk. It actually has some structure there. And by looking at these, we can tell a story about planet formation and solar system formation and relate it back to our own system. We also have all these telescopes that are getting better and better, coming online every day, and we can peer into these dusty disks using infrared. And the James Webb Space Telescope will help us do that sometime after 2018. So there's something that you guys need to know, first and foremost. I'm going to switch back and forth a lot, but I'm meaning the same thing. These are astrophysical disks, which means that there's some sort of disk that encircles some larger body, okay? I'm probably going to say astrophysical disk, dust disk, debris disk, rings, belts. There's a lot of names for these things, but they all have the same mechanics, the same dynamics. They may be made of slightly different material, but they're all basically the same. So in our solar system, we have planetary rings. This particular ring right here is Uranus. And this out here, taken by Voyager 2 quite a while ago, are these little tiny rings around Neptune. So even though there's planetary rings around every one of the giant planets in our solar system, but only Saturn tends to get the press. And so by studying these rings, we can learn how they form and that sort of thing. We also have other astrophysical disks in our backyard. Those circle around our sun. Those are the asteroid belt and the Kuiper belt. So in this lower graphic, you can see that this here is the asteroid belt. And you have the sun, and then Mercury, Venus, Earth, Mars, and the asteroid belt. And then Jupiter's orbit here. So if you zoom out a little bit more, so to get it in context, then we have Saturn, Uranus, Neptune, and then this whole Kuiper belt out here. And we'll discuss these throughout the day, but I just want to give you guys the context that these sorts of disks are everywhere. And one of the best places to study these disks is in our backyard. And it's beautiful, and that's Saturn. And so there's many ring regions that are changing on observable timescales. So many things in the universe happen in such long timescales that the human lifetime is the blink of an eye to that. But on Saturn, in Saturn's rings, things are changing on days, weeks, months, timelines. And so we can actually see these things, which is really exciting. The other thing is that the entire ring system formed with Saturn. And I'll talk a little bit more about that today. This is some new thinking in the community that the ring system is actually formed with Saturn. And this is a lot like planets forming with stars. Whole planetary systems form with their stars. And finally, structures in the rings reveal moons that we can't see with our instruments, with our telescopes, with our eyes. And so seeing these structures, we can infer some of the dynamics that are happening and really trace out a history of the evolution of Saturn's rings and of other disks in general. So this is why Saturn's ring system is really this great natural lab for studying disk dynamics. Not just planetary rings, but everything out there, including protoplanetary systems. So I want to give you guys a little primer first and foremost to let you know what kind of things I'm going to be showing in this talk. How we observe Saturn is really important here. So this top image is a Hubble image taken back in 2004. And that's of the big picture of Saturn. Okay, we can get a general context for Saturn there. And then in 2004, the Cassini mission, which is a spacecraft with a suite of instruments on board, came into the Saturn system and is now orbiting around Saturn and will continue to do so until 2017. So most of the images from this talk of Saturn are from the Cassini mission. And Cassini is great because it's around the planet, we get really up close and personal with those rings, and we can see a lot of smaller scale structures that we can't see with Hubble. So I want to give you guys a little quiz. Do you guys know what Saturn's rings are made of? I hear some ice. Okay. Okay, I hear rock too. Okay, so it's actually made of water ice, the same kind of thing that's in your iced tea on a hot day. And it ranges in sizes. So there's tiny dust sort of particles. There's things all the way up to the size of houses in there, okay? And as you can see from this artist's depiction, there's a lot of empty space between stuff. It's not some solid disk. It's not like a Frisbee. These ice chunks have wide distances between them. Okay, and these are constantly moving, smashing into each other. Some of those stick, some of those break. So there's this constant overturn in the material. So here's the Saturn ring system. And you can see that what you usually think of, I think most people think of as Saturn, is just this very small part, the B ring and the A ring here. And you have this whole slew of other stuff. We have, besides the broad dense rings, there's some gaps in the rings. There's these dusty components out here, several other rings even all the way out here. And that we're just finding out about in the last couple of years with Cassini even. And these beautiful, beautiful moons. So these moons are one of the first things that we can think of when we think about comparing Saturn to the solar system. We have things that are very familiar to us. For example, Titan. Titan has methane lakes. It has rivers and flowing liquid on the surface. It also has a thick atmosphere. While it's weird, it's not at all like the Earth in terms of its chemistry, but it's similar and very oddly familiar to us. We also have a moon that's geologically active. Enceladus here has, out of its south pole, has geysers. A bunch of individual geysers make up this overall plume. And that is water. And in fact, these geysers end up making up an entirely new ring around Saturn called the E ring that the little tiny Enceladus fits in right there. We also have other things that look similar to some of the other planets we're used to, things like Mercury, an airless body covered in craters, much like Venus here. Some people like to refer to it as the Death Star moon because of this giant crater right there. There's also Iapetus. And Iapetus is kind of interesting because it's an airless body and it's mostly icy, but it has this, on one side is dark and one side is bright. And that's because dust from a farther out moon is coming in and smacking into the backside of this moon. So we see these moons that seem familiar to us in terms of, it's a wide variety of things, always things. But we have to remember that Saturn is a ring moon system. So it has these moons interacting with the rings and doing kind of a cosmic dance. So I'll take you in, zoom in first to the B ring edge to let you guys see some of the structure that's being created. We're seeing the B ring edge here at equinox, which means light is coming in from the sun and is able to hit any vertical structure and produce shadows. That's what the dark stuff is down here. There are all these shadows being cast by vertical structure in the rings. So we're really seeing that Saturn's rings are not this simple disk that we thought they were. They have vertical structure. And that's all caused by this moon, Mimas. Mimas is far away, but it's tugging, always tugging on that B ring edge. So without even being able to see Mimas, we would know that it was there because of this structure. Much like this system that we've seen, here it's in a sub-millimeter wavelength. That's why it looks a little weird. It's not a big, pretty picture. But if you had the star right here, we see this dust disk around it. You can see there that that's not a pretty even disk. It's kind of lopsided, and these yellow parts are higher density clumpings of material. You can see over here, it looks like it may even be discontinuous. You know, there may be an open spot over there. So we know from looking at this that there must be a planet affecting this whole overall disk structure and evolution. And so, you know, by looking at Saturn's rings and figuring out what that structure may look like, comparing it to a moon, we can compare a planetary disk to an actual planet. So another spot in Saturn's rings that's really interesting is within the A ring, there are these gaps. There's the Keeler gap and the Encke gap. And the Keeler gap is really thin, really tiny. In fact, it's only 42 kilometers wide, right here. And the Encke gap is a little over 3 kilometers wide. So these are pretty small compared to the overall size of Saturn's rings. And you can see here that both of them have little tiny moons inside. And now these moons, Daphnis and Pan, help clear those gaps. And without seeing those little moons, which we didn't for a long time, we knew, for example, we knew that the Keeler gap existed. We've known that since Voyager. But we had no idea, we've never seen little Daphnis until Cassini got into the system. So we've only known about Daphnis for about 10 years, little less. So when we see a protoplanetary disk or a dust disk or a debris disk around another star, like you see here in this data, you can see this gap. And that tells us that there's a planet there. This is going to be a solar system someday. Oh, I mean, it's a solar system right now. But it's something that maybe doesn't look like our solar system, but there's still a planet there. This is a cleaned up artist's image of what's really happening. You can see where that gap is. So even though we can't see an actual planet, we know it's there. So the important thing here to know is that we know what moon-induced structure looks like. So that means that the planet's already there. But what happens if we're looking for smaller planets, much smaller planets, things the size of Mercury or the Earth, or if we're looking for areas that are building these sorts of planets? Well, we can look at the moons here and see that these moonlets, what I'm going to call moonlets, which are just very tiny moons, things like a mile in size, and these moonlet forming regions. So I'm going to take you through the propeller belt and the F ring. So the propeller belt also is in the A ring, where those gaps were. Interesting stuff happening in the A ring. So what we first saw in Cassini data was this image over here. So this is why it's important to turn off the lights in this room. It's a little difficult to see, even if you have it right in front of you. You have these little wings, what look like wings or propeller blades, in the data. And so I'm drawing your eye to them this way. You see it kind of has a propeller shape to it. And that's all because of a little tiny moon sitting right in the middle. Now, our instruments aren't good enough for us to be able to see a little moon. This moon is probably about 100 meters wide, so really small. But it's probably about 100 meters wide. But you can see it creates this structure. And then this is a different one. We decided to name the propellers after famous aviators, or in this case, an aviatrix. So this one is Earhart. And you can see this sort of vertical structure again, kind of like with the B-ring edge. You can see that these are perfectly observable to our instruments and to us at this level of technology right now. So we know what sorts of moons are being built in the system just by looking at the structure. And in fact, after we saw that one right here, we started to notice, oh wait, there's a whole bunch of other ones in the system too. If you zoom out into this section of the A-ring, you can see that there are actually several belts of these sorts of propellers. And then they all cluster in this little outer kind of middle of the A-ring here. So these are, very, very tiny areas, these three narrow bands where these propellers exist. But now we can narrow it down. We know where things, these sorts of structures are clumping. We know where a possible larger moon might have been that broke up and formed all these little moons. And conversely, where these little moons are now growing and becoming these larger structures like propellers. So now I'm going to take you to the granddaddy of moon formation, and that is the F-ring. The F-ring is my particular favorite. Zoom in a little bit here. You can already see that it looks weird. Something's weird about it. It's only 10 kilometers wide at that brightest point there. It's azimuthally asymmetric, which means it's not the same all the way around in the circle. And it has these two very tiny moons around it, Pandora and Prometheus. And Prometheus is particularly exciting because you can see it has an average radius of 45 kilometers. You can see it's just 136 this way, 80 this way, and then out of the board about 60 kilometers. It's not circular. It has a very strange shape, but its orbit brings it so close to the F-ring that it actually dips in occasionally and creates all sorts of strange structures. So this is a whole bunch of the different ones from the early parts of the Cassini mission. You have little knots that are brighter. And brighter material in these pictures means that it's denser. There's more stuff right there in that area. It has, you can see that it's broken up into what look like several different bands. Same here, and same here. And so that's Prometheus right there, dipping into the ring. So we have our own case study of how these sorts of things form. So I'll play this video for you guys, and you'll get to see Prometheus doing its thing, dipping into the F-ring. So it's important to know that we're focused on Prometheus this whole time. It's also moving with the F-ring, but it moves just a little bit faster. So it'll look in the movie like the F-ring is zooming by and Prometheus is standing still. That's just because we're centered on Prometheus the whole time. We're only watching Prometheus. So it comes up into the ring as part of its movement. And you can see some structure starting to form. The movie skips a little bit there, but you see that right there as Prometheus then moves away. So it does this over and over again. I'll play it for you guys again so you can see. It comes up, the F-ring looks pretty smooth all the way around this way, but then we get this area where it's pushed a bunch of ring particles together into this structure. And you can see at the bottom, this is the result of that. As Prometheus goes along, so Prometheus is way over here now, or way over here. You can see that you get these fans. It's called a fan structure. So I have a little cartoon of this. All of these ring particles get pushed together in these areas that I have boxed in here. You can see that they repeat fairly regularly, and materials pushed together in those spots. So when that happens, you could have material coming together. I'll show you guys up here. Watch the squared parts. You see those areas there where lots of ring particles come together, and then in other areas they're more spread out. Well, what could happen is these ring particles in those hit each other and break apart. They disrupt into a bunch of smaller pieces, and that's how those ring particles keep going. Or they could come together and stick to each other and become bigger and then move along. And if that happens a few times, maybe 10 times, you could build something that goes from 100 meters in size, something like what caused the propellers, all the way up to a moon, a real almost moon that's a few kilometers wide, a few miles wide, like this thing here. And we saw this guy. This is like the poster child for moonlet formation. We were actually able to see this guy back in 2006. He hung around for a year, almost a year. We were able to plot out a whole orbit. We went back and looked and found him, and we were very excited because we finally had proof that there were moons being built in Saturn's rings. And then after that year, disappeared. So what's happening is that these moonlets are coming together, clumping together, forming, and then it's possible that they hit each other as well and disrupt, just like that cartoon I showed you before. So Saturn's rings are continuously recycling in this way. And this is possibly how it happens in planetary systems, in protoplanetary systems, in these debris disks. You have this material come together, clump together, build small planets, planetoids, planetesimals. Some of those could break up, be destroyed, but some of them could persist, could stick together and really stand the test of time and become things like the terrestrial planets, or be those rocky cores for the giant planets that a bunch of gas collects around. So in studying Saturn's rings, we're really looking at a laboratory here for studying how other solar systems are made. And not just how they're made, but what to look for as we observe them. So we can tell which ones of these systems have planets. And we can learn a little bit about our own origins from tracing out things like gaps. Gaps that we're used to seeing around Saturn's rings, we can see around other planets. Little clumps that we see that are becoming moons around Saturn's rings, we can also see in the debris disks around other stars. So we really have a natural lab in our own backyard, and it's an exciting place to explore. Thank you.